Abendstern is being built with operations in mind, and a layout of this size would probably need about 6 to 8 operators and a dispatcher to run it smoothly. However, in India, model railroading is not a popular hobby, and I found it next to impossible to put together a group of operators. The next best option was to use a computer control system to take on the role of the operators and the dispatcher. The computer control system I am using is Train Controller Gold from Frywall Software. Train Controller Gold is in its 8th generation and is a very stable platform to control very complex model railroads. Before one jumps into the actual programming of the software, care must be taken to ensure the layout and its various components are functioning flawlessly. There is nothing worse than a stall or an incorrectly thrown turnout in the middle of an operating session to throw everything in disarray. Therefore, a lot of care was taken while installing the trackwork and the DCC system of Abendstern. To ensure the locomotives do not stall, I resort to different methods like using heavier locomotives such as this BR38 from Wayanad. All-wheel current pickups and jumper wires on this Kato rail bus and capacitors on this Izu locomotive all ensure stall-free operations. Rolling stock are weighted correctly as per the Fremo standards and resistors are installed to make them detectable on the layout. The programming of the software begins by drawing in the track plan and dividing the layout into various blocks. Once the blocks are drawn in, occupancy detection indicators are assigned to them and the actual lengths of the blocks along with braking distances are programmed. The software is then intelligent enough to calculate the routes between the blocks. Various elements such as signals, uncouplers and traffic control buttons are then fed in. Once everything is in place, various schedules are created which govern how trains operate between its origin and destination. Whilst I prefer to have individual schedules for individual trains, a single schedule can also be created for controlling many trains or locomotives. One such schedule is the Loco Shed or B-Way schedule, which controls a parade of locomotives through the loco service area. The loco service shed consists of 9 stalls, out of which 3 are external and are reserved for the diesels. Out of the 6 internal stalls, 2 are meant for the shorter tank locomotives, whilst the 4 longer stalls house the tender locomotives. The schedule has been programmed in such a way so that the 9 locomotives exit out of the stalls, traverse the turntable, and then head out to the 3 sidings at the other end of the shed area. Here the reverse direction and then head on back up the shed area and into the various stalls. By assigning the start and stop of the schedule to buttons on the screen, I can easily put into operation the entire schedule. When I want to end the session, I simply lock the exits. All the locomotives come to an elegant stop inside the stalls, waiting for my next command to start the schedule or to wrap things up. The operation or the waltz of the locomotives, as I like to call it, is best viewed in this time lapse. The power and adaptability of the software is further demonstrated in this sequence. A simple tap on the iPad triggers the schedule, which controls all the operations of a coal train to the other end of the layout and back. As the train enters the main station, it has to negotiate a double slip crossover and the yard ladder before coming to a halt in one of the yard tracks. Train controller very efficiently sets the route, changes the signal aspects, and brings the locomotive speed to the applicable limit of 40 km per hour. After bringing the train to a stop in the yard, the schedule now executes a series of commands and a macro which automatically uncouples the engine from its rake. The locomotive then runs around the rake to the other end of the yard. Once there, it reverses direction and recouples back onto the waiting rake. As a safety measure, I have to manually unlock the entry into the yard pocket. I do this only when I have visually confirmed that the locomotive has successfully uncoupled. Having run around and recoupled back onto the rake, the train is now ready for departure. Once again, I have to release the exit to the block manually, and the schedule then sets the route and the signals before driving the train back to the staging yard. The train negotiates the industrial and rural areas of the layout under complete command of the schedule and enters its designated storage track in the staging yard. The schedule will once again uncouple the locomotive from its rake, and after using the turntable as a switchback, it will then run around to the other end of the yard. Here it will reverse direction once again and then back up and recouple onto the waiting rake. Having completed the run-around maneuver, the locomotive backs onto the rake to recouple again. The whole schedule is now ready to repeat itself with a simple tap on the iPad. For the locomotives to operate precisely as we saw previously, it is absolutely essential to speed profile the locomotives. Speed profiling allows the software to understand the operating characteristics of the locomotive at various speed steps, thus allowing precise control over acceleration, deceleration, braking as well as starts and stops. The procedure begins by feeding in the data of the loco being speed profiled. I assign an icon, name and color to the locomotive and feed in its length and prototype tonnage. The icon and color helps one to identify the locomotive on the track plan and the route it is on very easily. The digital system I use is Digitrax Loconet. The class of the locomotive being speed profiled is BR03 and the last two digits of the road number is 49, hence the digital address of 349. I have a speed limit of 100 km per hour on my layout, and that is fed in as the top speed of the locomotive. Using ops mode programming and a HO scale speedometer from LS Digital, I set CV02 or initial speed step at a level so that the loco is able to crawl at its lowest speed in a smooth manner. Here it results in a scale speed of 2 km per hour. I then set CV05 or the maximum speed step in such a manner so as to set the top scale speed of the locomotive to approximately 100 km per hour. I then set CV06 or the mid speed step in such a manner that when the throttle is at 40% power, the scale speed is approximately 40 km per hour. Coming back to the speed profiling of the locomotive, the software offers various methods and I use the one involving 3 occupancy indicators. I choose on my layout a nearly 2 meter length of track with 2 adjacent stop indicators, which is ideal for speed profiling. The length of track, the run-out length of the locomotive, and the pause time is fed into the dialog box along with the digital address of the occupancy indicators. The threshold speed, or the slowest speed at which the locomotive moves smoothly, is then adjusted through the slider. This corresponds to the speed step value of 1, which we had programmed earlier into the decoder of the locomotive. Activating the start button initiates the speed profiling procedure. The software measures the scale speed of the locomotive at various speed steps, in the forward as well as reverse directions. The procedure takes about 30 minutes, so a time lapse is the best way to view it. Once speed profiling is complete, the brake compensation test needs to be conducted. This allows the software to control the braking distance of the locomotive. I choose a distance of 50 centimeters over which to conduct the brake compensation test and mark it out with the help of a measuring tape. I select the occupancy detection method for conducting the test and feed in the distance of 50 centimeters into the dialog box. It is important to ensure that the first wheel of the locomotive is detectable by the software. For times when there is no space for resistors, I simply use a resistance pane from Uhlenbrock. The contact spot is set at 2 centimeters, as that is the distance between the buffers and the first detectable point of contact. The speed at which I conduct the brake compensation test is again set at 40 km per hour. This is because 40 km per hour is the restricted speed on German railways, and most trains are travelling at this speed whilst entering a siding and are preparing to come to a stop. The procedure is more of a trial and error, and different values are fed into the software till we can get the locomotive to stop exactly at the 50 centimeter mark. Setting brake compensation at 0 results in the locomotive overshooting the mark quite significantly. The next brake compensation value I feed in is 20, and that also results in an overshoot of the 50 centimeter mark. A brake compensation value of 40 results in a pretty close stop near the mark. Finally, a brake compensation value of 45 gets the locomotive to come to a stop at exactly where we need it to be. After conducting the same test in the reverse direction, the locomotive is finally ready for service on the layout. Besides controlling trains and locomotives, the software also allows for excellent control over layout lighting, sound, and special effects. Elaborate switchboards can be created for the control of layout lights and sounds, and by programming various scenarios, one can create transitions from dawn to dusk. By DMX control over a smoke machine, fog effects also add a lot of drama. All in all, Train Controller Gold is an absolute joy to program and operate, and is the most complete solution for automatic control of a model railroad. Without it, Abendstern Nebenbahn would not have been possible, and I look forward to unearthing further possibilities on my layout with this software.